Okay, so what have we actually achieved now? We have defined a counter type that wraps such a function from int to a pair of an a and an int. We have wrapped that in a new type, and we've made that counter type an instance of the monad class. That is nice. I mean, it allows us to do this tree labeling thing, but actually this pattern is rather common. Now, unlike maybe, counter is not in our libraries. Instead, Haskell has a library with something which is slightly more general, and that is called state. And I want to show how we can generalize from our counter to the state that Haskell has. The general idea at first, the first step towards this generalization is that there is nothing really specific in the development that we have been doing about this type of the counter being an int. Of course, we need it to be an int because we want to increment it, right? But in principle, if we look, for example, at the definition of bind here for counters, there's nothing in here that makes any assumptions about the type of this state that is being passed on at all. We have an incoming C0, we send it here. We have an outcoming C1, we send it here. Right? We just pass this on. It doesn't matter whether this type here is an int or whether it's a string or whether it's something yet more complicated. Right? And similarly in return, we just pass on this piece of state. So we can generalize over it rather simply. So we can, instead of defining counter, we can define a type state as a and say something like make state, run state, and then we say s to a comma s. And then we could say type counter is just state applied to int. And now I'm getting an error because I have two versions of counter. So let's do it like this. Now, of course, if I want to generalize, I have to see it through. So I have to actually make the bind function more general. So everywhere where I have had counter, I now essentially get state. And here I can put state s as well. And of course I have to replace make counter with make state. And I have to replace run counter with run state. Okay. So now I still have lots of occurrences of counter here. I have step counter. I have to think about step counter again. Right? So for the time being, we can make step counter specific for the case that the state type is an int. And then we can define it like this, and that's fine here. The functor instance can just be for an arbitrary state s. The applicative instance can be for an arbitrary state s. And the monad instance can be for an arbitrary state s. Now what's left? We have an occurrence of run counter here in label tree itself, and that needs to be replaced by an occurrence of run state. And then, yes, okay, we do have a counter here. And actually, yeah, here I could just have left step counter to have the type counter int, because we defined this type synonym. And that is fine. And now once more, as so often before, I can do label tree example, and I can see that it works. Right? Okay. So far, so good. Now we still haven't used anything from the libraries, but now we are very close to what we have in the libraries. The only thing that we need to look at again is step counter. Because we have this general state type in the libraries and not the specific counter type in the library, step counter is not a primitive operation. Instead, what the libraries are offering for the general state situation is a function, or actually an action called get, that gives us access to something of type S. So similarly to how in the case of counter, where the state type is int, we get access to something of type int. Get gives us access to the current state, but it doesn't increment it, it doesn't modify it, it just gives us access to the current state. So how do we define get? Well, simply by make state, and then we get, actually I should in principle rename all these lambda c's with lambda s, but I'm not going to do that everywhere now. And we simply return the s as the result, and also leave the state unchanged. So this is just giving us access, explicitly access to the current state. Even though the threading of the state is implicit everywhere, if we explicitly want access to it, then we can use get. And there's a counterpart to this, which is put. And that allows us to replace the state with a new state. So we can completely replace something with a new state. So we have an argument s of type s here, and then we ignore the incoming state, and actually the result type of this is unit. We produce a unit result. And use the state that we have been passing into the put function as the replacement state. And these are two primitive operations, get and put, that we can use regardless of what the type of state is. We don't make any assumptions. We can always get access to the state, we can always replace it. And if we have these two primitive operations available, the nice thing is that we can now write functions such as step counter without breaking the abstraction and knowing anything about the internal representation of the state monad and the state threading that is going on. We can actually now just write step counter using do notation or using explicit binds. How do we do this? Well, we first do a get in order to get access to the current. In this case, step counter is still going to be specific to the situation that the state type is an integer. So to get access to the current counter value, we use get for this. And then we increment the counter by putting back c+1. And then we are returning c. So we get access to the current counter value, which is c, and that is what we ultimately return. So we return the current counter value. But before we return it, we actually increment it by 1. So together, these operations do exactly the same as the old definition of step counter did, but we have defined them just in terms of get and put. And get and put are general functions that work on the state type, that do not make any assumptions about what the type of the specific type of the state is. And with this definition of step counter and this definition of get and put, everything still works. All right. So now we're basically at a stage where we can just move to the libraries. So let me look at our Cabal file. that we have here. So we are depending on base and the containers package already. So the library that we're going to use now is called transformers. So transformers is a package on Hackage that is defining all sorts of monad related tools. So it's actually a rather sophisticated package. And it's called transformers because actually everything internally is defined not in terms of plain monads, but in terms of yet a slightly more advanced concept that is called monad transformers, that is allowing us to combine different monads with each other. Okay, so the actual definition of state there is also yet slightly more general than what I have shown, but the interface to it is almost exactly the same. So let's go back here and let's import control monad trans state. And I think Haskell language server has not picked up the change. So let me try to restart to make it pick up the change in the Cabal file. And now I get all sorts of problems listed, all sorts of errors, but this is coming from the duplication now, that because I have been importing a state type, so the import is now no longer problematic, but I'm also defining my own. So there is a lot of stuff that I can now get rid of. So run state is now ambiguous, right? Because it can refer to the run state that I've defined here and to the run state that I've imported. So basically, I can just remove the definition of state that we have. I can leave the type synonym for counter, because that is not defined in the library. I can get rid of this bind definition. I can get rid of this return definition. I can get rid of get and put. I can keep step counter, because that is still specific for our counter type. I can get rid of our own functor applicative and monad instance. And this one was commented out anyway. And now everything works. Right? So I don't have to change any code in label tree or label tree awks. And, everything works as before. I need to restart Cabal REPL here as well to pick up the changes in the Cabal file. But now it does work. And once again, I can call label tree example and it works. But now it works with the library-based version of state. Okay, so indeed we now have functions get and functions put that are coming from the library. And you can see this because they actually have more general types. They mentioned this state TSMS and state TSM unit. But whenever you read state TSM with an additional monad constraint, you can, for the time being, just read state, because actually state in this library is a type synonym where state T is instantiated to S, which is the state type, and to a type that we have not been discussing, which is called identity, but it is a relatively boring type. And the interface of state, of the special case of state, is exactly the interface as we have been discussing it. In particular, there is also this run state function that is taking a state SA, using the type synonym, and a state to a pair of an A and an S, like we had, so that we can extract the first component. Actually, the fact that we're extracting the first component and discarding the final state, as we're doing here, is so common that there is a specific function in the library for just this special case, which is called eval state, which is taking this additional first component in the end. So it just goes from state SA, takes an initial state, and gives us the final result, and automatically discards the final state. So we could actually simplify this definition here by using eval state, and it would still work. So in this way, we can use something from the libraries, which is, of course, much more convenient and is even more general than what we have been discussing, because if we wanted to have a different state type, then we could still use exactly the same mechanism. Okay, that concludes what I want to say about the state type and its monad and applicative instances. And now it's time to reflect a bit, which I'm going to do in the next video.